My name is Mwila Nyurongo, and I am the lecturer for Programming Foundations at Lusaka Goldsmiths University. Welcome back. Today, we are diving into the core building blocks of procedural logic in TypeScript. Building on our introduction to variables and basic types, this lecture, which is modeled after MIT's course, focuses on how we handle text, interact with users, and implement branching logic to make our programs dynamic. By the end of this session, you should be comfortable manipulating strings, managing input and output, and directing program flow through conditional statements. For today's agenda, our roadmap is divided into three primary modules. First, we will examine strings, which TypeScript treats as a sequence-based object type for text representation. Second, we look at input and outputs to see how our programs can communicate with the outside world. Finally, we will cover branching, the mechanism by which our code makes decisions and deviates from a strictly linear execution path. As a quick refresher from the previous lecture, in TypeScript, every object has a specific type. This type is essential because it defines the set of operations the computer is allowed to perform on the specific object. The core primitives we deal with most often are string, number, and Boolean, a critical distinction for those coming from languages like C or Java. TypeScript does not distinguish between integers and floating point decimals. They are all simply of type number. Unfortunately for you, if you're coming from no programming experience, just know that floating points are decimals. To store data, we use variables, which effectively bind a descriptive name to an object residing in memory. We declare these using let for values, where that might change, and const for immutable bindings. While TypeScript is excellent at type inference, which means it can often guess the type based on the initial value, we can also use explicit type annotations to ensure our code remains robust and self-documenting. A string is defined as a sequence of characters, and it is important to remember that these are case-sensitive. Strings can contain anything from standard alphabet letters to special symbols, spaces, and numerical digits. In TypeScript, you can define a string using either double quotes or single quotes, allowing for flexibility when your text itself might contain a quotation mark. The most basic operation we perform on strings is concatenation, using the plus operator when you add two strings together. The runtime creates a completely new object in memory that contains the characters of both operands merged together. For example, concatenating me and myself results in the new string, me myself. If you want a space between them, you must explicitly concatenate a space character. While some languages, like Python, use the star operator for string repetition, TypeScript follows a more method-oriented approach. To repeat a string multiple times, we use the built-in .repeat method. For instance, calling me as a string literal .repeat3 will generate the string me. This is a more explicit way of handling sequence repetition that aligns with TypeScript's object-oriented nature. One of the primary advantages of TypeScript over plain JavaScript is static type checking. The compiler will prevent nonsensical operations at compile time before your code even runs. For example, if you attempt to multiply a string by a number, TypeScript will flag this as an error. This safety mechanism catches bugs like typos or logical errors that would otherwise only surface as confusing runtime failures. To determine the size of a string, we access its .length property. It is important to note that this is a property, not a function call, and it evaluates to a value of type number. For a string like ABC, the length is 3. This is a fundamental operation when you need to iterate through a sequence of or validate user input. Because strings are sequences, we can access individual characters using square bracket notation. Like most modern programming languages, Typescript uses zero-based indexing. This means the first character is at index 0, the second at index 1, and so on. For the string ABC, S is A and S is C. What happens if you try to access an index that doesn't exist? If you have a 3-character string and try to access index 31, Typescript will not typically crash your program with a hard error. Instead, the operation evaluates to undefined. While this prevents an immediate crash, it can lead to logic errors down the line if you don't handle that undefined value property. Passing a negative integer to the .at method allows you to count backwards from the end of a sequence. For example, s.at -1 will always return the last character, and s.at -2 will return the second to last. Often you don't just want one character, but a whole segment of the string. This is called slicing, or extracting a substring. In Typescript, we use the .slice method in where we send the start and end arguments. A crucial rule to memorize: the start index is inclusive, but the end index is exclusive. So s.slice 3, which is our start, and 6, which is our end, will extract the characters at indices 3, 4, and 5. The .slice method is quite flexible. If you omit the second argument, the end index, Typescript will assume you want to slice from the start index all the way to the end of the string. Conversely, if you want the first n characters, you can slice from 0 to n. For example, s.slice 0, 3 gives you the first 3 characters of any string. A vital concept in computer science is immutability. In Typescript, strings are immutable, meaning that once a string object is created in memory, it cannot be modified. You cannot execute a command like s is equal to b to change a single letter. If you want to change a string, you must instead create an entirely new string object by combining pieces of the old one. To communicate results to the user, we use the console.log function. It is important to understand that in a compiled code file, simply typing an expression like 5 plus 2 will perform the math, but the result will never be visible to the user. You must explicitly pass the expression to console.log to print it to the standard output. The console.log function is quite versatile. It can accept multiple arguments separated by commas. When you do this, Typescript will print all the objects on the same line, automatically inserting a space between each one. This is often cleaner than manually concatenating everything into one long string, especially when mixing strings and numbers. Moving beyond static data, we need to consider how our programs interact with the outside world. In a browser-based environment, we can use the prompt function to capture user input. However, there is a critical type safety detail to remember. Prompt always returns the input as a string, or null if the user cancels. Even if a user types a number, the runtime treats it as text, which is a common source of logic errors in early programs. Because prompt returns a string, we cannot immediately perform mathematical operations on that input. If you try to multiply a string number, you might run into issues. To resolve this, we perform a typecast using the number constructor to convert the string into a formal number type. Only after this conversion can we safely perform mathematical multiplication or other arithmetic operations. In order to format string literals, TypeScript offers template literals. By using backticks instead of standard quotes, you can use the $ curly brace syntax to interpolate variables and expressions directly into a string. This is significantly more readable than manually concatenation and automatically handles the conversion of non-string types into a string format for display. Now we shift towards control flow, which is built upon the Boolean type. A Boolean has exactly two possible values, true and false. These values are usually the result of comparison operators. For instance, evaluating whether 5 is greater than 3 results in the Boolean value true, which testing strict equality between two different numbers. The most frequent syntax errors in programming is confusing the assignment operator with the equality operator. A single equal sign is used for assignment, which is binding a name to a value. In TypeScript, we use the triple equal sign for strict equality. This ensures that both the value and the type match, which is the industry standard for preventing subtle bugs. To build complex logical conditions, we utilize a standard suite of comparison operators. These include greater than, less than, and their equal to counterparts. We also have strict equality and inequality. Every one of these operations evaluates to a Boolean, which our branching statements will then use to make decisions. We can combine multiple Boolean expressions using logical operators to form more sophisticated conditions. The not operator, or the exclamation mark, flips a Boolean to its opposite. The double ampersand, or the AND operator, returns the true only if both operands are true, while the double pipe operator, or the OR operator, returns true if at least one of the operands is true. Understanding these is key to managing complex state transitions in your code. Let's look at the practical application. Suppose we are checking a student's schedule. If we evaluate sleep time is greater than pset time, we get a Boolean result. In this case, false. Similarly, if we have two Boolean flags, drive and drink, we can use the double AND operator to determine if it's safe for both to be true at once. Since one is true and the other is false, the combined result is false. Standard code execution is linear, moving from the top of the file to the bottom. Branching allows us to break this linearity. By using conditions, we can tell the program to skip certain blocks of code or choose between different paths in TypeScript. These paths or blocks of code are defined and scoped using curly braces. The if statement is the most basic branching primitive. It evaluates a condition in parentheses. If the condition is true, the code inside the following curly braces executes. If the condition is false, the program simply skips the block and continues with the next line of code outside the braces. To provide an alternative path, we use the else keyword. This creates a fallback block that only executes if the initial condition evaluates to false. This structure ensures that one of the two blocks will always run, but never both. For example, we can branch to print big number or small number based on a single comparison. When you have more than two mutually exclusive possibilities, you can chain conditions using else if. The program checks these in order to execute the code block for the first condition that evaluates to true. Once a match is found, all subsequent else if and else blocks in the chain are ignored. Consider a scheduling script where we check the sum of pset hours and sleep hours. We first check if the sum exceeds 24 hours to catch impossible scenarios. If not, we check if it exactly equals 24 for a full schedule. Finally, the else block catches any remaining case where free time is available. Logic isn't always flat. You can place an if statement inside another if block. This is known as nesting. This allows you to perform secondary checks only if a primary condition is met. For instance, you might first check if two numbers are equal, and then only if they are, check if they are non-zero to calculate a ratio. As your branching logic becomes more complex, code readability becomes paramount. While Typescript uses curly braces to define blocks, consistent indentation is the standard for making the structure visible to human developers. A big idea for this course is to debug early and often. Test your branches with various inputs to ensure that edge cases are handled correctly. In summary, we've covered strings as immutable sequences of characters indexed from 0. We've looked at inputs and outputs, noting that the prompt function always gives us strings, while the console.log function handles our output. Finally, we explored branching using if, else if, and else to control program flow, based on Boolean logic. In the next session, we will expand on these foundations. We will look at a more advanced branch logic and introduce the concept of loops. Loops will allow us to move beyond just making single decisions to repeating commands efficiently, which is where true power of automation begins. See you then.